Okay, let's increase the complexity of our models by introducing the concepts of heterogeneity and transmission matrices. What does it mean heterogeneity? Until now, we assumed that the transmission rate was the same for every individual in our population, and also that every individual could get in contact with everyone else in the population independently from their social status, their age, their position, etc. This, of course, is a big assumption. Therefore, it's usual to include heterogeneity in the models in order to relax these assumptions and reduce biases. What are the heterogeneity sources? Well, there's a lot of them. Age is one of the more important because it can impact both the transmission rate beta by changing the number of contacts or the susceptibility to infection, and both the infectious period gamma, since older people may stay sick for a longer time. The behavior, that is how many contacts a person have and the kind of contacts this person has with other individuals, especially if we speak about, for example, sexually transmitted infectious diseases. The living environment, if you live in a place with a high density of population or lower density of population, of course, if you live on a mountain, you have a much lower risk of getting infected than living in the city center. Whether you use drugs, they can change both beta by changing the probability of getting of transmitting the infection, for example, the antiretroviral drugs for HIV, or they can decrease the period of infectiousness gamma, 1 over gamma. The immunity status, this is connected also with age. So the people with a lower immunity level, with immunodeficiencies, for example, are more susceptible to infection than healthier people. Again, a typical example is people with HIV, which get also more susceptible to fungal infections. And there are a number of other possible examples. But let's start simple. To explain some basics regarding heterogeneity in infectious disease model, we can start from a classical SIS model. That is a model in which infected people go back to be susceptible. There isn't any kind of immunity. This kind of models usually is used to describe sexually transmitted diseases, since very few of them do provide some kind of long-lasting immunity. So in this simplified model, we will assume that there is a high-risk group H, which is smaller in numerosity, and a low-risk group L, which is much higher in numerosity. And as I said, there is no lifelong immunity. In this model, since there is no immunity, we consider that the change in susceptible is just the opposite of the change in infectious people. Okay, this is a diagram of the model. We see that we have two groups of individuals, the high risk and the low risk, and we have the people in the susceptible people in the high risk can become infectious people in the high risk group. The same for the susceptible people in the low risk group. But then we have the infectious people in the high risk group can either infect other people susceptibles in the high risk group or infect susceptibles in low risk group. And the same is for the people infectious people in the low risk group. So we have a sort of cross effects, cross infectious risk. This cross infectious risk usually is described as a transmission matrix that we observe here. So instead of having one beta, like we had in the previous models, we have a matrix of betas. A matrix means a group of elements, not just one. And we can see here that we have at least 4 betas. So the betas of the high-risk infectious people that infects the high-risk susceptible people. the beta of the high-risk infectious people infecting the susceptibles in the low risk group, the infectious people in the low risk group infecting those the susceptible in the risk group, and finally the infectious people in the low risk group infecting the susceptible people in the low risk group. And this is how the usual SIS model is modified when we have heterogeneity. So remember that usually the change in the number of infectious people is equal to beta by the proportion of infectious multiplied by the number of susceptible. In this case, this term is we have it twice, because we have the infectious that come from the high-risk groups and the infections that come from the low-risk group. And then we have the gamma for the high-risk group. And the same happens for the low-risk group. So instead of having one flow for the infectious people, we have two flows, one for the high-risk group and one for the low-risk group. It may seem complicated at first glance, but it's not as complicated as it looks. So when we have G risk groups, in this case two, we automatically have G by G matrix. So in this case for 2 by 2. So if we had 3 risk groups, then we will have a matrix with 9 betas and so on. The number of betas increases exponentially as the number of risk groups that we are considering. This kind of transmission matrices are also called who acquires infection from who matrices. So there are differences in the trajectories of the epidemics once we consider heterogeneity. In the case of the SIS model, we can observe 3 phases of the epidemic. Let's see how do they work. At the beginning of the epidemic, we can simulate putting a small number of infectious people both in the low risk group and the high risk group. And we can see that in the high risk group, we have an initial explosive increase in the number of cases, a so-called exponential phase. But in the low risk group, we have instead observe a decrease in the number of cases. This is expected because the low risk group has a R naught which is lower than 1, and the high risk group has a R naught which is higher than 1. We will see an example later. But after a while, we can see that both trajectories start to get in correlation. What is going on here? It happens that the smaller number of people in the high-risk group who get infected are able by themselves to carry on the epidemic in the whole population by also infecting the people in the low-risk group. This is the so-called slaved phase of the epidemic. Eventually, we reach an equilibrium phase, which is stable, since this is there is no immunity for this infection. So what about R naught? In this case, there are actually many of them. We have the initial R naughts, which are, as we saw before, relative to the initial phases of the epidemic. And let's see how can we compute them. So, as we said, we have high-risk group, which is smaller, 20% of the population, and a low-risk group, which is larger, let's say 80% of the population. And this is the transmission matrix. So we see that the high-risk people in the high-risk group infect each other with high efficacy. They also affect people also in the low-risk group infect each other, but with a lower efficacy. And there is also some spillover transmission across groups. So this is the high-risk group towards the low-risk group, and this is the low-risk group towards the high-risk group. In this case, we keep gamma equal to 1 for simplicity. And this is how we compute the R naughts for the two groups. So the R naughts is just the weighted average of the betas for each group. So for the R naught for the high-risk group is just the weighted average of the betas adjusted by the numerosity of each group, of each target group. The same is for the R naught in the low risk group. We can observe that, as we saw in the picture before, there is a quite large R naught in the high risk group, 2.08, which is above 1, so it predicts an increase in cases. But a lower than 1 R naught in the low risk group, 0.82, which again predicts a decrease in cases as observed in the initial part of this graph. Okay, but then there is also a general R naught, which is valid for the whole epidemic, for the whole population. Well, to calculate this R naught, we need to consider the proportion of infectious individuals in the slaved phase. Actually, we need to compute how the infectious individuals distribute between the two groups. So, IS is the number of infectious individuals in the slave phase. We want to compute the proportion of these individuals in the high risk group and in the low risk group. Unfortunately, this computation is not easy. We need something called matrix algebra and eigenvalues to do this, so we will not describe the process here, but we will just report the results. And it's possible to observe that the general R naught is again a weighted average of the individual group R naughts, weighted by how the cases are distributed between the two risk groups. In this case, it's equal more or less to 2. You can notice that it's more or less in between the two groups R naught. So what can you derive from this example? Each risk group drives an initial R naught, which is linked to the group relative proportions in infectiousness, so the beta and the betas and the n. But there is also a general R naught which depends on the infection proportion between group during the slave phase. Let's observe instead now the epidemic equilibrium, so the last part of this course. If we were working with an unstructured model, so without heterogeneity, we would expect that the proportion of susceptible at equilibrium will be equal to 1 over R naught, which in this case, using the example from the slide before, since R naught is equal to 2, we will expect a 50% number of susceptible at equilibrium situation. Instead, the reality is quite different from this. So to calculate the actual fraction of susceptible in equilibrium, first we need to calculate the fraction of infectious people at equilibrium. In this case, with the numbers from before, these fractions will be 1% of the population, 10% of the population considered in the high risk group, and 3% of the population considered the low risk group. These numbers they cannot be computed analytically. You need to use a numerical solution because there are quadratic equations involved which cannot be just solved by pen and paper. You need a computer to do this. But we did the calculus for you. So then using this number, the final computed number of susceptible over the total, it's 86-87%. As you can see, we just used the number of people in each group and removed the people that is infected in both group, and then take the proportion over the total. This number, 87%, is much higher than expected for such an higher R0, which is 50%. Well, how do we interpret these numbers? So it happens that the small high-risk group drives the high R naught in the whole population, but since the small high-risk group is a minority of the population, the overall prevalence will still be low, because the low-risk group keep the equilibrium prevalence lower than expected. But even if this prevalence is low, the small risk group is enough to keep the epidemic alive through something called a spillover effect, since a small number of infectious people in the high risk group is able to infect a large number also in the low risk group. And this produced the high R0, R0 that we observe in the slave phase. Which are the consequences of this for infection control, especially through vaccination? Well, surprisingly, even if the fraction of susceptible at equilibrium is different once we consider heterogeneity, their immunity threshold is the same. It's still 1 minus 1 over R0. So if we just vaccine people at random, we need to cover a fraction of the population which is equal to this number. But if we start to target the high risk group more than the lower risk group, we can reach the immunity threshold at a much lower percentage of vaccinated population. Let's see an example. Let's take an R0 in the slave phase equal to 2.25. And again, we have the population which is divided in 20% of high risk group and 80% of low risk group. It can be shown through calculation that I won't show here that we can reach the herd immunity threshold by vaccinating either 55% at random, as shown by the formula here, or by vaccinating 75% of people in the high risk group and 40% of people in the low risk group, which overall equate to 47% of the population, which is lower than 55. So we can show that when there are different risk groups in a population, it's always better to target with more intensity the smaller high risk group than the overall, the just vaccinated people at random, because this will allow us to reach the herd immunity much faster. Until now, we observed a certain level of contact between groups. The contact between groups is exemplified by the numbers in these diagonals in the transmission matrices. But different scenarios can have different level of cross transmission between groups. For example, in this situation, we have a level of transmission between groups which is 1/5 of the transmission in the high-risk group. But in this other scenario, we have no transmission at all between groups. So we have like a population in which there are two different groups that totally don't have, get in contact with each other, and they cannot transmit the infection with each other. The level of segregation between groups is called assortativity. When we have high assortativity, it means that there is no connection between groups, and this phenomenon can be summarized by a variable called alpha. It's possible to show, but we won't see the calculation here, that as the assortative index alpha increases, also the basic reproduction number on the overall population increases. And therefore, the different degree of assortativity index means different epidemic dynamics. So high assortativity increases the R0. And this happens because infectious events are not wasted on the low risk one. So the people in the high risk group always spend time with the other people in the high risk group, maximizing the diffusion of the pathogen. They don't waste time infecting people in the low risk group that then will not create a longer chain of infection. Sorry. Another thing to notice is that when there is high assortativity, it gets less relevant to target the vaccination towards the high risk group, because even if we need to block the epidemic separately in both groups, because there is no spillover effect between the two of them. Finally, let's give a look at age contact patterns. They are much used in during epidemiological studies because it's known that the level of contacts changes a lot when considering ages, both when considering contacts between peers, but especially when considering contacts between people of different ages. You can see here in this picture taken from a paper from literature that it's expected to have a high level of assortativity. That is, people tend to spend time mostly with people of the same age. But we also have some cluster of contacts, even between different ages. One very common cluster are the contacts between the parents and their children. It's the same here. This matrices are specular. Or we can see a school that there is much contact among peers of the same age, but totally no contacts with other people of different ages apart from the teachers. This is UK, so the teachers are usually younger than usual. And while if we take instead all the other environments, there is a much more mixing between age groups. It's also interesting to see job places in which also there are interesting patterns of contacts. It's very important to consider these contact matrices because they can explain a lot about epidemics. For example, it's known that for flu, old people are at risk because they get infected by their grandchildren, who themselves get infected at school. So there is this flow of the pathogen that grows up in the schools where there are a lot of contact and then reach the parents through the contacts between grandchildren and the grandparents. And it's possible to have a large number of age group to consider. In this case, we have almost 20. And as I said before, then the number of transmission parameters to consider grows exponentially with the number of risk groups that we are considering. And so when you have too many risk groups, it gets easier to consider an alternative modeling called the continuous compartments, which we will not show in this presentation. That instead of having a lot of compartments and a lot of exponential number of transmission parameters, we have a bidimensional distribution of the transmission risk according to for example, the age.